In the depths of the Abell 3627 cluster, a structure is moving that breaks the usual understanding of the shape and stability of galaxies. ESO 137-001 is hurtling through the incandescent plasma of the intergalactic medium at such a speed that the medium itself becomes an instrument of destruction and transformation. The huge cloud of hot gas that fills the space of the cluster is not a void. It is dense on the scale of space, saturated with particles heated to millions of degrees, and it is in this invisible ocean that the process begins that turns the galaxy into a stream of light and matter. As they move through this medium, the outer layers of the galaxy's gas experience a pressure comparable to a continuous impact at cosmic speeds. The gravitational structure holds the stars together, but the gas component is much more vulnerable. It separates, stretches back, forming long plumes that go hundreds of thousands of light years. These plumes are not static formations. They live, pulsate turbulently, contract, tear apart, and reassemble into complex patterns where magnetic fields are intertwined with plasma flows. Inside these tails, a process takes place that contradicts the usual logic of exhaustion. Instead of the final disappearance of matter, areas of compression are formed where the gas begins to condense again. New star systems are born there, despite the fact that the environment looks aggressive and destructive. These zones become sources of radiation recorded in various ranges, from X-ray to optical. The X-ray glow shows the boundaries of the interaction between the ejected gas and the hot medium of the cluster. At the same time, the main disk of the galaxy remains its spiral structure, but loses some of its material. The outer arms are deformed, their density decreases, and the internal dynamics become more concentrated. In the center, the rotation of the star system continues, where gravitational equilibrium still keeps the structure from complete destruction. However, the process of losing matter continues continuously, and the tail becomes more complex, layered, and extended. Temperature differences between the galactic gas and the environment create shock fronts. These fronts compress matter, causing local bursts of radiation. In these areas, energy is distributed unevenly, forming density waves that propagate along the tail. The magnetic fields present in the galaxy are stretched into long filaments that bind the individual plasma fragments into a single dynamical system. The tail that forms behind a moving galaxy is not uniform. It has high-density nodes, rarefied zones, turbulent vortices, and long flows in which matter gradually cools. These regions can stretch for hundreds of thousands of light years, forming a structure that is larger than the galaxy itself. Despite this, the origin of all this flow is associated with one source, a gravitationally bound system passing through the dense medium of the cluster. Within these extended gas structures, chemical evolution takes place. Elements ejected from the disk of the galaxy mix with the matter of the intergalactic medium. New combinations and density fluctuations are formed, which become the basis for future star formations. This process is not uniform. Some parts of the tail remain rarefied and hot, while others gradually transition to colder states, allowing gravity to begin assembling new structures. X-ray observations capture not only the tail itself, but also the compression front in front of the galaxy. There, the gas of the intergalactic medium condenses, heats up even more, forming a shock wave that surrounds the front of the moving system. This region becomes a place of extreme physical conditions, where pressure and temperature reach values rarely found even on the scale of galaxy clusters. The internal dynamics of the disk does not stop. The spiral arms continue to rotate, but their structure becomes asymmetrical. The side facing the motion is more strongly affected than the opposite side. This leads to a gradual shift in the distribution of gas within the galaxy, enhancing the effect of pulling material in the direction of the tail. Over time, the tail begins to form a complex network of filaments. These filaments do not exist in isolation. They interact, intersect, and create areas of increased density. In some of them, signs of star formation are recorded, which makes the tail not just a trace of destruction, but at the same time an area of creative processes. The energy of the galaxy's motion through the medium is converted into structuring of matter on a huge scale. The plasma inside the tail is in a state of constant instability. Magnetic lines are stretched and torn apart, creating local bursts of energy. These processes result in an homogeneous distribution of radiation, where bright areas alternate with almost transparent areas. As a result, the tail acquires a complex internal texture that resembles a flow in which each part is in its own dynamic state. The gravitational field of the galaxy itself continues to hold its core and part of the disk, but gradually loses control over the outer layers of gas. This process is not instantaneous. It stretches for hundreds of millions of years. During this time, the structure of the tail can change many times, moving from dense, bright configurations to more rarefied and diffuse states. Over time, the elongated flow of matter ceases to be perceived as a simple continuation of the galaxy and turns into an independent dynamic system within the environment of the cluster. Inside it, particle collisions continue. Turbulent movements intensify, and energy is redistributed between layers of gas with different densities. In the densest nodes, local cooling begins, which allows gravity to reassemble matter into clumps capable of eventually giving rise to new stellar structures, despite the fact that the original material has already been torn from the main disk. Temperature heterogeneity becomes a key factor in the existence of the tail. Hot areas retain a high degree of ionization, emitting in the X-ray range, while cooler areas begin to glow in the optical and ultraviolet ranges. This creates a complex, multi-layered picture where the same flow of matter exists simultaneously in different physical states, distributed over space depending on local conditions of pressure and density.
Internal magnetic fields, stretched out by movement through the intergalactic medium, form long filaments that stabilize part of the tail structure. These filaments act as guides for the plasma, limiting its chaotic expansion and creating preferred channels of motion. At the intersection of magnetic lines, areas of increased activity appear, where energy is concentrated and then released in the form of radiation flashes. The galactic disk, which has lost part of its gas, is gradually changing its evolutionary trajectory. A decrease in the supply of cold matter affects the future ability of star formation within the system itself. However, the core remains stable due to the dominant gravitational potential. The rotation of the stars continues almost unchanged, although the outer envelope becomes increasingly rarefied and asymmetrical. The front of the system, colliding with dense intergalactic plasma, forms a shock arc. This region is characterized by extreme gas compression, where the pressure reaches values that can completely change the state of matter.
Here,
They are heated to temperatures at which atoms lose electrons, turning into a completely ionized medium. This boundary between the moving galaxy and the outer gas becomes a zone of constant energy exchange. The tail continues to increase in length, following the trajectory of movement. Its shape does not remain stable. Turbulent vortices break the continuity of the structure, creating separate fragments, which then reconnect under the influence of gravity and magnetic forces. These processes create the impression of live dynamics, where each part of the system is in constant change. In some areas of the tail, the density of matter reaches critical values at which cloud fragmentation begins. These fragments gradually condense, forming protostellar structures. Although they form outside the main disk of the galaxy, they inherit the chemical composition of the original material, enriched with heavy elements ejected from the inner regions of the system.
X-ray observations reveal the complex structure of the interface between the tail and the environment. There are mixing zones where the hot gas of the accumulation penetrates into colder streams, creating transition regions with dramatically changing physical parameters. These areas are unstable and subject to constant changes related to pressure dynamics and flow rates. The gravitational influence of the cluster plays the role of an external framework within which all this evolution takes place. It not only keeps the galaxy inside the system, but also determines the nature of its motion. The trajectory passes through the inhomogeneities of the medium, which intensifies the processes of compression and pulling of matter, making the tail even more complex and extended. Over time, the structure of the tail can reach scales comparable to the distances between galaxies within a cluster. It becomes not just a trace of movement, but a significant component of the general dynamics of the environment. Inside it, the processing of matter continues, passing between states, temperatures, and densities.
The energy released during the interactions inside the tail is dissipated into the surrounding space, affecting the local thermodynamics of the cluster's environment. This results in regions where temperature and density deviate from the average background, creating inhomogeneities that can persist over long cosmic time intervals. Internal processes in the galaxy and its tail remain interconnected despite the loss of matter. Gravity continues to hold the system together, but the balance gradually shifts towards external influences. In the end, a structure like this becomes evidence of the interaction of motion, medium, and time, where form is determined not by a static state, but by a continuous process of transformation of matter. Gradually, the tail ceases to be a single continuous stream and begins to break up into a complex hierarchy of structures, each of which lives according to its own local physical conditions.
In some areas, hot, rarefied plasma, almost completely ionized and held only by the magnetic fields of the cluster, dominates. In others, there are cold condensations where the gas has already begun to transition to a molecular state. These contrasts form a network of intersecting flows within which energy is distributed extremely unevenly. Along the entire length of the tail, zones of shock waves are recorded, which occur where individual clumps of matter collide with the environment or with each other. These waves compress the gas, locally increasing its density and temperature, resulting in short-term bursts of radiation. After passing the shock front, the matter expands again, but in a changed configuration, with redistributed internal energy and a changed structure of magnetic lines. Internal magnetic fields are becoming an increasingly important factor in stability. They stretch into long fibers that link individual areas of the tail into a single, albeit highly unstable, system. These fibers not only direct the movement of plasma, but also keep fragments of the structure from complete decay, creating temporary frameworks on which dense knots of matter are formed.
Some of these nodes are beginning to show signs of gravitational collapse. The gas in them is compressed, loses heat energy, and becomes more and more dense. Within such regions, the germ structures of future stellar objects are formed, despite the fact that they are located far beyond the main disk of the galaxy. These processes show that even under conditions of destruction of the original structure, the local ordering of matter continues. The very motion of ESO 137001 through the intergalactic medium remains the driving force behind the entire system. The gravitational field of the cluster directs the trajectory, and the resistance of the hot plasma creates constant pressure on the outer layers of the galaxy. This pressure is uneven. It depends on the local density of the medium, which leads to an asymmetrical pulling of the gas and the formation of a complex, curved tail structure. Within the galaxy itself, the redistribution of matter continues. The loss of the outer layers causes the remaining gas to concentrate closer to the center.
This intensifies the internal processes of star formation in the core, where the density remains high enough to continue the gravitational collapse of the clouds. However, the external areas are gradually becoming impoverished, and their contribution to the overall dynamics of the system is decreasing. The temperature gradients between the tail and the environment are becoming increasingly sharp. At the points of contact between the hot gas of the cluster and the cooler galactic matter, thin transition layers are formed, where physical parameters change over short distances. These layers are unstable and prone to the development of hydrodynamic instabilities, which further complicate the structure of the tail. In some regions of the tail, the phenomenon of recompression of matter is observed. After the initial destruction and pulling, the gas can be concentrated again under the influence of local gravitational centers.
These centers arise due to density inhomogeneities left behind by the passage of shock waves. As a result, compact clouds are formed, which can exist relatively autonomously within the general flow. Tail radiation becomes multi-component. The X-ray range captures hot, rarefied regions. The optical range captures denser and cooler structures, and the radio range allows you to track the distribution of magnetic fields and synchrotron radiation of charged particles. The totality of these data forms a picture in which the same object exists in several energy states at the same time. The dynamics of the entire system remains unstable on large timescales. The tail continues to change shape, disintegrate, and reassemble into new configurations. The gravity of the cluster, the motion of the galaxy, and the pressure of the intergalactic medium are in constant interaction, creating a complex system of forces, for no component remains static.
Ultimately, such structures become important elements in the evolution of galaxy clusters. They redistribute matter between galaxies and the intergalactic medium, affect plasma thermodynamics, and create conditions for local star formation outside traditional galactic disks. In this process, destruction and creation become inseparable, and the shape of the tail itself becomes a reflection of the continuous exchange of energy and matter within the large-scale structure of the universe. As the scale and time of interaction increases, the structure of the tail begins to obey not one dominant dynamic, but a multitude of overlapping processes that act simultaneously and often in opposite directions. Turbulence becomes not just a disturbance, but the main mechanism of the existence of matter in this elongated flow. Vortices of various sizes arise, disintegrate, and form again, creating a cascade of energy transitions from large structures to small ones and back again.
In the most rarefied regions of the tail, the gas gradually mixes with the intergalactic medium, losing its original belonging to the galaxy. However, complete dispersion occurs unevenly. Residual magnetic filaments hold fragments of matter, creating long, thin structures that can persist for millions of years. These filaments act as a framework along which a slow redistribution of density continues. Inside the denser nodes, the cooling process continues, which leads to further compression of the substance. Where the temperature drops low enough, molecular clouds are formed, capable of gravitational collapse. These regions become local centers of new star formation, despite the fact that they exist in an environment that is initially unfavorable for the sustained accumulation of cold gas.
Galactic motion through the hot environment of the cluster enhances the effect of drifting matter. The front of the system is constantly under pressure, which not only compresses the gas, but also redistributes it over the surface of the disk. This leads to the formation of asymmetric structures within the galaxy itself, where one side is more depleted and the other retains most of the dense matter. The interstellar orbits remain relatively stable, but the gas component continues to change. The flows of matter inside the disk become more directional, with a clear shift towards the tail. This creates a constant source of replenishment for the elongated structure, even as the gas reserves in the galactic body are gradually depleted. X-rays capture the boundary between a moving galaxy and its surroundings as a complex, multi-layered region. There is a constant interaction of flows with different temperatures and densities. Shock waves do not form a single line, but break up into a network of curved fronts that propagate across the interaction surface.
In this zone, there is the development of instabilities that lead to fragmentation of the boundary. Higher density matter penetrates the less dense medium in the form of finger-like structures, while the surrounding plasma flows around them, creating complex hydrodynamic patterns. These processes enhance the mixing of matter and accelerate the transformation of the tail structure. Over time, the tail becomes not just a trace of movement, but a full-fledged dynamic component of the cluster. It affects the distribution of energy, density, and magnetic fields in the environment. In some region clusters, such structures can interact with each other, creating even more complex configurations of gas flows. Within the galaxy itself, the central region continues to gradually densify. The loss of external gas leads to an increase in the relative density of the core, which can intensify the internal processes of star formation. However, this process is limited by the amount of cold matter remaining and is not able to compensate for the global mass loss.
The tail, in turn, continues to evolve. Its structure becomes increasingly fragmented, but at the same time retains the general direction set by the movement of the galaxy. Individual fragments can break away and exist as independent clouds of gas within the cluster, gradually dissolving or participating in new processes of compression and cooling. Magnetic fields continue to play a stabilizing role, but their structure is becoming increasingly chaotic. Lines of tension intertwine, break, and reconnect, creating a complex network in which energy is unevenly distributed. These processes affect the nature of radiation and plasma dynamics at all scales. In the long term, such systems become a mechanism for the redistribution of matter within galaxy clusters. Matter torn from one galaxy does not disappear, but is included in a general recycling cycle, where it can become part of new structures, clouds, or star systems. Thus, the tail ceases to be just a trace of destruction and turns into an active element of cosmic evolution.
Over time, the structure of the tail reaches a state where the distinction between individual fragments of matter and the environment becomes almost blurred. The boundary ceases to be a clear line and turns into a complex area of gradual transition, where the parameters of the gas change continuously without sharp breaks. This condition occurs due to repeated mixing of flows, repeated shock waves, and constant exposure to magnetic fields that redistribute energy at all scales. Within the most stable fragments, slow gravitational compression continues. These regions are becoming more and more compact, and in some of them, long-lived dense cores are formed, which can survive even after the partial destruction of the surrounding gas. Such structures can undergo significant changes in the external environment, remaining bound by their own gravity and local magnetic configurations. The main flow of the tail gradually loses its original homogeneity. Instead of a single elongated formation, it becomes a system of filaments and clouds distributed along the trajectory of ESO 137-001.
These filaments no longer form a strictly continuous line, but retain the general orientation given by the movement through the dense medium of the cluster. Inside each filament, local processes of cooling, heating, and redistribution of matter continue. The intergalactic medium through which the system passes also does not remain passive. It responds to the passage of the galaxy by changing the density, temperature, and turbulence pattern. As a result, a long trace of disturbances is formed, which persists even after the bulk of the gas has already left the interaction region. This trail becomes part of the overall dynamics of the cluster, affecting the subsequent movements of other objects. As you move away from the center of the cluster, the influence of external pressure decreases, and the tail structure begins to gradually expand. However, this expansion does not lead to an orderly decay. On the contrary, it increases fragmentation as different parts of the system react differently to a decrease in pressure. Denser areas retain coherence, while rarefied areas begin to dissolve into the surrounding space. Internal magnetic lines, stretched over huge distances, gradually lose their original order. Reconnection of magnetic fields becomes a frequent phenomenon, accompanied by local energy emissions. These emissions affect the dynamics of the plasma, creating new perturbations that rearrange the tail structure again. Thus, the system remains in a state of continuous processing of itself. Star formation, which occurs inside the densest fragments, gradually changes the chemical composition of the surrounding gas. The resulting stars begin to emit energy that affects nearby regions, heating them up and partially preventing further compression of matter. This creates local zones of equilibrium between gravitational collapse and energetic heating. Over time, the tail ceases to be solely a consequence of the movement of the galaxy and becomes an independent structural element of the cluster.
It participates in the redistribution of mass, energy, and magnetic fields, linking different regions of the intergalactic medium together. In this state, it can no longer be separated from the general dynamics of the system of which it is a part. The final stage in the evolution of such structures is not the disappearance, but the dissolution of the differences between the components. The gas that once belonged to the galaxy gradually becomes part of the general background of the cluster, retaining only traces of its former organization in the form of inhomogeneities of density and magnetic configurations. These traces can last much longer than the original form itself. Thus, the tail, which arose as a result of movement through the hot intergalactic medium, turns into a mechanism for the redistribution of matter on a gigantic scale. It connects the processes of destruction and creation into a single chain, where each stage becomes the basis for the next. And in this continuous movement of matter, the main feature of such systems is preserved: constant transformation without the final disappearance of form.